So let me remind you that after this lecture, there's going to be a picture outside. So the last speaker this morning is Andrea City. So he's PhD in Paris with Francesco company. And now he's chargé de recherche CNRS in Grenoble. So we're going to talk about the asymptotic plateau problem in hyperbolic.
Thank you for the presentation and for the invitation to this exciting school. I wish this school like that had existed when I was a student, but I also hope this will continue. So I know everyone is tired and wondering whether it's worth listening to this talk, or maybe it's a better idea to think about something else. So I give you a 3-minute teaser, and then you will decide whether you want to continue watching or not. Okay. So the playground will be the hyperbolic space, which is, well, the ball endowed with a metric, which, well, is the usual quantum metric. Just a reminder. Okay, so it looks like a ball. It has a complete Riemann metric in the interior. The boundary of the hyperbolic free space is here. It's a conformal sphere. And here's a theorem by Anderson, 83. So for any Jordan curve, lambda in the boundary at infinity of H3. So Jordan curve is just the image of a continuous injective map from the circle. Pick any Jordan curve like that. The theorem says there exists a minimal disk sigma inside A, such that its asymptotic boundary, so meaning that its closure in the closed ball is equal to lambda. Okay, so there exists a minimal surface, which is actually fixed. One can also take it to be stable, but it's not important for the moment, which fills this curve. Okay, but so sigma is not unique in general. May not be unique. May not be unique. Okay. So the questions that I want to talk about in this talk. So the first question is, under which conditions is sigma unique? Can we say on lambda so as to ensure uniqueness? And the second question is about how many solutions can we have. So we'll call, so this problem, I will call it the asymptotic plateau problem, meaning that it's about solving like the plateau problem, filling a curve with a minimal surface, but the curve is infinite. So sigma, I will call it a solution of the asymptotic plateau problem. And so the second question I want to address is, when not unique, well, how many solutions can we have? So while you may like it or not, but that's what it will be about. So now I start the actual talk. And I want to give some motivation, some special situation on this problem, which is important for me as a motivation. And this is about quasi-Fuchsian manifolds. So this will be related to what Gabriella has talked. And actually, it's funny because, like Gabriella, I also was not raised as a differential geometer. So I usually post my papers on the archive in another section, but in my case, it's the geometric topology section. So I can't avoid talking about group action. Yeah, I can't avoid talking about group actions in this talk because this is sort of where my background is. So let's say let gamma or A subgroup gamma of the group of isometries of H3 is quasi-Fuchsian, so it's a quasi-Fuchsian group. If by first gamma as a group is isomorphic to the fundamental group of a closed oriented surface, orientable surface, homogeneous of these two. And second, so there exists a C inside H3, which is convex, that gamma acts on this C serves this convex subset, geodesically convex subset, and the action is free properties continuous. And go back. Okay. So there is that. Oh, well, okay. Let me first learn something before going on to the picture. So consequences of this definition are that the quotient manifold is what is called the quasi-Fuchsian manifold, which is homeomorphic to S times R. So S is the surface, okay? And the second definition.
So co-compact seems like the wrong word. This is not a compact, you know.
No, but it acts co-compactly on some subset.
Okay, so.
Okay, let me write a line and then I'll draw a picture. And the second consequence is that what is called the limit set, lambda of the group, is a Jordan curve. And what is the limit set? The limit set is the following thing. You take accumulation points of the orbit of any point. This doesn't depend on the orbit. Okay. And take the closure. Okay. So now I'll draw a picture. Okay. So what happens is that we have a gamma invariant convex subset C. That is actually the smallest one, but it's not very important. Closed, and the action is co-compact on this guy. So the quotient is something like this. Homeomorphic the product, and it has a chunk which is convexic, geodesically convexic. And the picture really looks like that in the sense that the limit set is a Jordan curve. So what is the limit set? You take any point in the interior, over H3, whatever you want. Okay. Look at the orbits by the group. Since the action is properly discontinuous, this only accumulates at infinity, and the accumulation points is Jordan curve. The closure of the set of accumulation points. So in this context, so there exists not only there exists a minimal disk which fills the curve, there always exists one which is gamma invariant. Wait. Figure sigma, right? To the Jordan curve, which is the disk. Okay, is This could be proved in many ways, but okay. And an important thing is that this guy, sigma, right? So this guy is always contained in any C as an definition. So by the maximum principle, the minimal surface, any minimal surface must be contained inside any such invariance.
So, okay. I mean, this is a statement in terms of S times R, the existence of a minimal surface in it that's embedded in S, right?
Yes, exactly. It's just that I don't want to formulate it like that but it's the same thing. Basically, this result is basically saying that there is a minimal surface in the homotopy class of the horizontal surface.
But in terms of uniqueness, already there's a difference with if the Hausdorff dimension is close to 1, then maybe there's uniqueness, and if it's far away from 1.
Yeah, I'll get to this, but yeah, I don't want to spoiler too much. Yes, it's this sort of where I will be going with. That's exactly the point. Okay. So actually, I will first give some answers to question 2. Time permitting, I will move on to question 1. So actually, I will not have a final answer of this Q2, but I want to give examples and explain what can happen. Okay, so some examples. Okay, so the first example is a very simple one. We take lambda to be just a round circle. Just take we can take any intersection with any plane. For example, an equator. These are indistinguishable from the isometry groups and any round circle to any other. Okay, so in this case, there is one clear solution, which is a totally generic copy of H2 inside H3. Okay, I will call it that actually P, isometric H2, and P is the unique solution. Just because it must be contained in any convex subset having this curve of infinity because of what I just said. And there is one smallest one which is evident here, is just plane. So the only possible solution is the plane itself because it must be contained in the plane. Okay, so this is good. Okay. It's a case where we have uniqueness. Now I will say something which is not quite an example. So consider the following situation. So we consider lambda to be a disjoint union of 2 round circles. One. Yes. So this is not the asymptotic plateau problem the way I formulated it, because it's not a Jordan chord, it's a 2 Jordan chords. But I want to talk about it anyway, because it will be a preparation for what comes next. Okay? So Ci round circles. So we have a sort of solution in some sense to this problem, which is we can take 2 totally geometric planes. Okay? 1, 2. Okay. But sometimes, so there is also another one, which is, so it's a fact, if these 2 circles are close enough, and to measure how much 2 circles are close, I actually measure the distance between 2 planes. So if the distance between P1 and 2 is less than some constant delta, which I don't remember how much it is, it's a universal constant, then there exists a minimal catenoid calligraphy C, which looks something like this, with boundary, asymptotic boundary of this minimal catenoid equal to the disjoint of C1, C2. Maybe I don't want to call this lambda. I will use lambda for Jordan chords. Okay. And what is a minimal catenoid? A minimal catenoid, so it will be a surface of revolution along the common perpendicular. So along with respect to the common perpendicular. One. So when you have two planes in A, this is hyperbolic geometry, when you have two planes in H3 such that the boundaries are disjoint, then you can always find a common perpendicular. So the picture is really, geometry, the picture is really like that. Okay? So you can then rotate by one parameter group of rotations along this axis. And if the distance is close enough, then you can find the rotational invariant solution. Okay. Yeah, so this is apparently not related in any way to the asymptotic plateau problem. But instead it is because now I will use it to construct an example of a curve that has a Jordan curve that has several solutions. So now we'll take lambda with at least two solutions. How is this constructed? So the curve has to look like that. Okay. And I want to be able to put a pair of minimal catenoids in these positions. So I want to be able to have a minimal catenoid here, which looks like that. It goes into interior. We have two circles here. Let's call this C0. And I want to be able to put a minimal catenoid also here. C1. C1. So in order to be able to do this, I must make sure that the two circles are close enough. So maybe I have to take this strip, make it very narrow so that these two circles are close, and make these two vertical segments also very close so that these two circles are close enough. I can do it. But I keep drawing like that, for otherwise we won't see anything. But imagine these two are very close and also this is very thin. All right? So the claim, I mean, I will not give many proofs actually, but the idea is that one can construct two solutions. So sigma 1, which is contained, or maybe sigma naught, contained in H3 minus C naught. Sigma 1 contained minus C1. Okay. And this is how they look like. So the one which is in the complement of C naught, I will just draw, I don't draw H3 anymore. I just put this. So the one in the complement of this catenoid topologically looks like that. Basically, we take the ground floor here. We take the ceiling of the lower floor. Okay. It's difficult to draw. And then we connect by a little band here. Okay. So I say it in words again. We take the ceiling of the upper floor. We take the ceiling of the lower floor, the ground of the upper floor. This is to this, and then we connect it here. Okay, and this will be disjoint. So here, basically, when you want to construct a minimal surface like that, what you have to do is to use this catenoid as barrier and sort of construct it in a complement. But you can do it, and it will be in the complement of this C. Okay, and the other one. The other one will instead look like, well, you just stay on the side. This will be in the complement of the catenoid. good. Believe me that you can construct these things, then one can show that sigma 1 is different from sigma 2 by topological reason. So the reason is that colors. So I go back here. So the reason is the following: is that we can draw two curves inside a closed ball. One curve is doing this thing, divide the perimeter, and then enter into the catenoid. It enters into the tunnel and then it stays on the side. And this one, on the contrary, does that, and then enters into the tunnel. Okay. So these two curves, I draw them here. One is like that, and the other one is like that. Maybe let me stay below. The other one is like that. Okay. The important thing is that these two are linked. Okay, in our tree. And so this allows one to show that these two are distinct. So basically the argument is that if they were the same, then they will constitute a topological disk which lives in the complement of both catenoids with this curve at infinity. And this is forbidden because these two curves are linked. Okay, so this is the bad. This is the bad example. We have an example of non-uniqueness. And there is a theorem, like 2015, says for any n integer number, there exists a quasi-Fuchsian group gamma such that where the corresponding set lambda of gamma admits at least n solutions and gamma invariant solutions of the asymptotic problem. And the idea is to, well, exploit this strategy and improve it. So the idea of the approach is to do the following. Is to do, well, the same thing, but many times. So now we don't have just one floor, we have many floors. It's like a parking with many floors. Okay.
Different.
Again?
Asymptotic curves with the asymptotic curves on this plateau are different for the solution.
No, but I'm not done yet. I'm not done yet. So I take K of them, and then I connect by a little band. Maybe let me do it with another, like a different color, and then I connect with a little band here on the back. Okay, so now it's a Jordan curve, it's connected. And then you do this in such a way that you have these catenoids at every level. Okay. So now basically at every level you have two choices. So you can construct 2 to the power of k pairwise distinct minimal risks. So basically what you do is you make your favorite choice. At every level you choose either the left one or the right one. Okay, you do this at every level. You have 2 to the power of k possible choices. And then you construct your minimal disk according to this rule. So basically, if here you pick
you want to choose the limit set to the Hausdorff close to what you do.
You're going too fast. Give me a second. Give me a second. Okay, it's not yet, but you're totally right. This is not yet a quasi-Fuchsian limit set. But let me do it anyway. So what you do is at every level, you imagine you picked this one here. So what you do is ground and ceiling, right? Because you want to be in the complement of this one. Imagine you've chosen at this level here, you've chosen the other one, then what you want to do is you stay on the side. Okay. And then you do this according to all the choices, and then you sort of connect to a little band in the back. And then again, there's some work to show that you can actually do a minimal disk, which is topological like that, but it works, and the pair was distinct by the same topological argument. And then, okay, this is not the limit set of a quasi-Fuchsian manifold, but then what you can do is then.
Can you remember the limit set here?
No, I can write this sentence. Then one can approximate say epsilon close this lambda by a quasi-Fuchsian limit set, like the limit set of a quasi-Fuchsian. So this will never be the limit set of a quasi-Fuchsian manifold because it's piecewise smooth, and the limit set is never piecewise smooth except when it's totally geodesic. Okay. But what you can do is that you can find the limit set of a maybe very, very large genus quasi-Fuchsian group, which is very, very close to here. As close enough so that it still avoids all these circles. Okay. And so you can basically do the same thing, but instead of the piecewise smooth curve, you take this one, which is maybe it's sort of fractal, but it has the same behavior.
But as n goes to infinity, do the Hausdorff dimensions of these limit sets actually?
Yeah, I think so.
Close to 2?
Yeah. I really think so. And then, actually, this procedure has no control on the genus, by the way. Maybe one could do something better and do some control on the genus in terms of the number of minimal surfaces you want to construct. But anyway, so we have 2 to the power of k. So at the end, there exists n, which is greater than 2 to the power of k. Okay, and now I want to give the final example, but I will call it a theorem. So the theorem is that exists a Jordan curve lambda that needs probably many pairwise distinct solutions. So the proof idea is to what happens? I try to use the same picture. No, this one will have nothing to do with positive, and I will tell you why. So the proof idea is we do the same thing, but infinitely many times. Okay, so we keep going closer and closer. We do the same thing on both sides. And then, okay, let me draw a picture in the other model. Okay, so here we basically have not only K, but we have like infinity many. I'll draw a picture now I use the C, so in the boundary of the upper half space model, C infinity, okay? So it's a plane with one point at infinity. So the picture looks like that. We have to play the same game. Let me make this here. Okay. Okay. Then we connect with the band to the interior and to the exterior. And then we continue. Then we keep going. Of course, it's very difficult to draw reasonably. All right. And so this is just a line, an embedded line for the moment, but then we add 2 points. So add 0 and infinity. So we add these 2 points. We add these 2 points here, and now lambda is a Jordan curve. So lambda is a Jordan curve. But this is not hard, sorry, to show. We can make it invariant by this scaling here if we want. It helps, but it's not really necessary. Okay. And now we play the same game, but now we have. Okay, so this is the statement. Ooh. Now for any. So here we have catenoids. All levels. So now I need an index. I will call this catenoid here at the ith level. This catenoid will be J is J level. This will be Cj naught, and this will be Cj1. Okay. So for any function f from z to 0, 1, one can construct sigma f minimal disk which lives in the complement of H3 minus the union of all these complements. So minus the union J and Z of C, J, F, J. So, and they're pairwise distinct. So if one is different than F2, sigma F1 is different than sigma F2 by the same, or whatever, by the same topological area. If the two functions are different, they are different at least one J, and at this J, the two cores that are linked, then you run the same argument. So they must be different. So this is the proof of the idea of the proof.
Why uncomfortable?
Yeah, sorry, I forgot to say that. Okay, so at the end, we have 2 to the power of Z solutions. Maybe this is not very orthodox. Anyway, this is uncountable.
For any game, you go for the
Yeah. Okay, this is uncountable. Okay. To the development of digital numbers. Okay. So So
Is there a direct link between this construction and what you, I mean, if you take quasi-Fuchsian groups, you can take limits where you get, in the end, something which covers a compact free manifold with fibers over a circle?
No, that's not related to this. No, because in that case, the limit set will be sorted everywhere. So no, it's not related to that. And I will also answer to former Gabriella's question. So we can't, for this curve here, we can't approximate by but we can do the same thing. We can't approximate by quasi-Fuchsian limit set because this one is not disquisite. So this approximation thing goes back to Poincaré. Basically, takes some circles and takes the group generated by reflection in these circles. But you need to be able to put basically circles which cover this by circles where every circle will intersect the previous and the next, and you won't be able to do this around 0 to 50. So you can't do the same thing with quasi-Fuchsian. So this is why it only holds without any group action. Okay. So you might have guessed that I like movies. When I was young, I was a big fan of spaghetti western, this is Sergio Leone. And then years later, I found out that these spaghetti western movies were not shooted in the far west. They were shooted in Andalusia. So here we have very good.
The bad and the ugly.
Very bad. And then I don't know if this one is good or bad, but it's certainly not nice. And well, probably only people from certain age on are laughing. Okay. So the topological argument is the following: is that let me do it in the general case here. So you have two functions, f1 and f2, that are different. Okay, so they are different at some level. So at some level, they differ on one choice. Okay, and then what you do is at this level, you draw a curve, which in one case it goes inside this tunnel. Okay, and then it stays on the complement of the curve. Okay.
So, are these joined?
No, this you can't say. They are disjoint. Okay, let me just finish because then I can answer better your question. So then you do the same thing with the other catenoid here, and you have this curve. Okay, so the curve stays in the boundary except when they cross the catenoid. So we have these two curves, which one is like that, the other one is like that, but then here it goes like that. Okay, and these are linked. So you can't have basically a disk in a complement form. They are not disjoint. What you can say is that basically if F1 is bigger than F2, in the sense that for every I, for every I, Fi of I is bigger than F2 of I, then they are disjoint. But so you get only what we can prove is that only countably many of them are pairwise disjoint.
Okay.
Because then this like that you can only do a countable.
I think the thing was that people catch is that these are actually disjoint from certain disks, right? When you have a solution, you're drawing something that's
but then you want to know if they're pairwise disjoint between them, and then you can only make sure if basically always stay left and at some point you get bigger and then you stay bigger. Other questions? Okay. So in the remaining time, I will discuss some answers to question 1. So in particular, I will try to give some criteria that ensure uniqueness. So here the starting point is this Uhlenbeck program, so it's a theorem by Uhlenbeck. So she gave a criterion for uniqueness in the quasi-Fuchsian manifold, but I will still state it above just to be consistent. So the criterion is the following: if gamma is a quasi-Fuchsian group, a gamma invariant solution sigma such that there is a condition on the second fundamental form, so the norm of the second fundamental form squared is less than 2, then sigma is the unique solution among gamma invariant ones. So let me, how much time do we have? Like 20 minutes, right? Or start with. Yeah. Okay, great, thanks. Yeah, sorry, I don't know why I was looking at you. Say it again?
My definition is
yeah. So let me make a couple of remarks on this, and then I will tell you, I mean, how we sort of improve following these ideas, but improve this result. So first remark, so this condition here is basically telling us that, so this is lambda 1 squared plus lambda 2 squared, or lambda 1 and lambda 2 are the principal curvatures, but these are opposites, so this is 2 lambda squared. Okay? So this less than 2 is saying that the principal curvature is less than 1. And the remark is that this condition here implies stability. This condition is stronger than stability. And this is, we have seen this many times. So if these days, so if we have some sigma, we do a compactly supportive variation that comes from Q times the normal. Q is compactly supported, sigma. And the second variation, the area of sigma t intersected with the big compact region. Okay, so this is equal to what? Is equal to minus the integral of sigma of u L of u with respect to the area of sigma, where L of u is the Laplacian of sigma of u plus, then you have the Ricci plus the norm for square. Okay, so this is, we are in a hyperbolic space, so this is equal to -2, so this is negative for every u. So L is negative definite. This is negative definite, and you add something negative. So this is a condition which is very strong, stronger than unique than stability. And the second remark I want to make is, well, why did Uhlenbeck care about it? Her program is about sort of understanding quasi-Fuchsian manifolds through these minimal surfaces. And the remark is saying, hey, if we have this bound on the second fundamental form, then there is a unique minimal surface in the quotient manifold. So instead of studying the manifold, we can just study the minimal surfaces that are inside there. So her remark is that we have this almost Fuchsian space. So it's the space of almost Fuchsian matrix. On the product, modulo isometry. For some technical reason, we want to quotient only by diffeomorphism, Uhlenbeck by diffeomorphisms, which are isotopic with identity. This is just to make this space a manifold instead of having singularities. Yeah. So almost Fuchsian is what I was about to say. Almost Fuchsian means that it is quasi-Fuchsian plus contains the minimal surface. Satisfying. Okay. So this space you can embed it, and this is what Gabriela explained. You can embed in the cotangent bundle of the vector space. This is vector space. space of conformal classes or matrix modulo if not of S. Okay? And the embedding is like, okay, you take, so you have a matrix here up to diffeomorphisms as a topic to the identity, and here there exists a unique sigma. I'm doing everything in a quotient, so I associate. No. In this theorem, there is a unique one. This is really unique. If I have time, I'll talk a little bit about it. So this is just to say that this is just to make anyway the link with this Uhlenbeck program. So given such a metric, what she did is take the conformal class of the restriction of the metric to the minimal surface and some alpha, where alpha is some holomorphic quadratic differential square such that the real part of alpha, which one can do with the surfaces being ones. Okay, so this metric is injective. And so instead of starting the manifold, one can just basically fix in regular space. And I want to mention a nice theorem, which is recent by Bronstein and Smith. So let's call this, I don't know, phi. So the image of phi is convex in any fiber. Just fix the point here. You look at the image inside the fiber, it's a convex of so one can start using, lots of information and technology from vector space to start these methods. Okay, anyway. Yeah. I'll now give a couple of results. And maybe I have time to talk about some ideas of the proofs and the role of stability, among other things.
There's an old observation due to Bayes, which is that when you're looking at quasi-Fuchsian groups, it's really parameterized by Teichmüller space times Teichmüller space.
Yes.
You have a formal structure of gen. Is there any direct knowledge of how this image of phi sits in that picture?
Yeah, it's a good question. No, I think it's difficult to give some information. One can say something. So basically, one can, if you know a bound on the second fundamental form, then you know the Teichmüller distance between these two Bayes parameters. So you can sort of compare the subset in the cotangent bundle to this subset of Teichmüller times Teichmüller. But it's not, there's bounds, there is some information, they're not explicitly related. Okay, so one theorem that we have proved is we have improved this criterion without any group action. So if lambda is Jordan curve admitting a solution sigma such that phi always again, then sigma is the unique solution. And here we can also improve small or equal. No, sorry, okay, but there is something. This is not entirely true. So this is not for any Jordan core. We must suppose that this is a quasi-circle, which is a particular subclass of Jordan cores. So if you know a little bit about quasi-conformal analysis, this just means that it's the image of a circle by a quasi-conformal map. If you don't know what this means, you completely forget about it. But this is first of all, this is satisfied by all quasi-Fuchsian limit sets. So this is a clear generalization. And actually, this condition can be replaced by a weaker condition, so by having finite width. It may be easier to imagine. So you have the Jordan curve. You take C. You can take the smallest convex subset. So basically the convex R. And the finite width condition is that this quantity is associated to lambda. So this is the picture is following. You take any point in the interior. You look at the distance from each component by the Jordan Schoenfeld theorem, whatever this has to connect. This has two boundary components. Convex body is pole and complement of Jordan coordinate pole is two connected components. So you take the supremum for all x inside this C, or the distance between x and one boundary component plus the distance between x and the other boundary component. This is a minus plus. This is boundary plus of C, and this is boundary minus of C is the interior. Okay, so the condition is that this is finite. It's just sort of more intuitive, and this is implied by being a quasi-circle. It's stronger. Sorry, yes. Yeah.
So X is in the interior of the space, or
no, in sorry, in the yellow C. Okay. In the convex half. Huh?
Convex setting.
Okay.
I didn't understand. Sorry. It's in the interior of H3. Yes. Yes. Yeah. So it's the interior of the convex half. Yeah, you're right. Convex half would contain a curve. Okay. And this notion of width was constant. So okay, that's nice, but still, that theorem of Uhlenbeck and this generalization is sort of unsatisfying, sort of artificial, because you're looking for a condition that ensures uniqueness of a solution. But actually, to verify this condition, you must know one solution. So basically, what you need to know is that there is one. You need to know one solution. Know this has this condition. It satisfies this condition, and then you will know that's one. One would like to have some condition which is more intrinsic on lambda, and here is the theorem. So basically, I proved this uncountably many years ago for stable, and then together with the same authors, we proved that the general case, so it's sort of combination of the two. So there exists some universal constant epsilon naught greater than 0, such that lambda in the boundary of H3 is a 1 plus epsilon. Here I can't define it, sorry. But the 1 plus epsilon quasi-circle for epsilon less than or equal to epsilon naught. Then lambda emits in solution.
This is the distortion on the quasi.
Exactly. So this is saying if the Jordan curve is the image of a quasi-conformal map whose distortion is at most 1 plus epsilon, then this is unique. So this is a sort of way, this epsilon is a sort of way of measuring distance in the space of all Jordan curves, if you want. Okay, if they're close enough in this weird metric space structure to a circle, then you have a unique solution. So sort of the idea is, in the case of the circle, you have a unique one. If you deform it a little bit but in a uniform way somehow, then it will stay unique. And in fact, So the proof, why one can prove this. So in fact, one shows that the norm of the second fundamental form is controlled by a universal constant times this epsilon. Okay. So the idea is really that this epsilon allows to control the width. And if one controls the width, so it's basically the minimal surface. Remember, the minimal surface is always inside the convex set. So the idea is if one can control the width, then one can control the curvature. And so one can make this less than 2 for epsilon, but it's stronger than universal amount on the second fundamental. Right. Okay. I have 5 minutes left. So in these 5 minutes, I will, maybe even less than that, I will sketch the proof of this.
So does the proof lend itself to trying to get an effective estimate of the size of C, or is it proof by contradiction?
No. I mean, no. It's not a proof by contradiction. It's a proof which is direct, but it involves some a priori estimates that at some point at some point require to take some constant which you don't know how much. So the control on C is not explicit, but the proof is not by contradiction. I mean, the proof by contradiction would tell you probably that the normal second fundamental form is bounded by some function of epsilon, but this is stronger. This is a linear function. So sketch the sketch is the following. So the first step is the following. So it suffices. Oh, that sigma is a unique stable. I claim that to prove the theorem, it's enough to show uniqueness in a smaller class, in a class of stable solutions. There is always one stable solution. It will suffice to show that there's the only one. And the reason is, I'll do it pictorially. It's a very simple one. So we have a Jordan curve. Okay. So imagine we have a solution. Imagine we have some solution sigma naught, which is not stable. And then what you do is you use it as a barrier, and you manage to construct two others, sigma 1 and sigma 2. So this one, let's say, is unstable. Suppose there is such an unstable solution, but then you can sort of use it as a barrier to construct other two, which are stable. Okay. So they must, okay, these two must be disjoint by the strong maximum principle. Otherwise, they would coincide with sigma naught, but sigma naught is unstable and they're stable. So okay. Now, second step is, okay, now let sigma prime, by contradiction, another now stable solution. Now we suppose there is another stable solution. Okay. And the observation is the following, is that this condition on the second fundamental form, so this is now sigma, okay. This condition on a stable fundamental, on the second fundamental form, gives some information on the equidistant surfaces. So this condition less than or equal to 2, this implies that the equidistant surfaces T, so sigma T are those that one can take the subset which is taking the distance T, let's say on one side, maybe of sine distance, whatever, the equidistant surfaces from sigma. So this condition ensures that these surfaces are embedded. So basically there is no calculus and inconvex. Inconvex meaning that the mean curvature vector is pointing in the interior, okay? Pointing towards sigma. Maybe it's a little unusual.
You just got
No,
perpendicular.
No, it's not that. No, because you just move perpendicular, exactly. You start from a point and you move perpendicular. You exponentiate time t. Now, it's not the same because these ones change the conformal class along when you flow normally. Okay? So, if.
You don't hit any conjugate points here.
Exactly. You don't get any conjugate. That's exactly. And this is an easy complication because of the condition. This is Uhlenbeck was the first one to observe this. It was the key. So now, consider the f, which is the function from sigma prime to r. So f is the distance from sigma. Okay, so it's a restriction of the distance function from sigma. By contradiction, on the other solution that one imagines to have. So if f has a maximum, and so at the maximum point, so if this distance has a maximum, at this point here, the mean curvature vector is pointing inwards, but this one should be the yellow one should be minimal, and this gives a contradiction. Then contradiction. The maximum principle. Okay. So the last step, 3. So if the maximum on the super sigma prime of f is not achieved, then what one does is one use stability. So this is important. This supremum is always finite because of the finite width condition. Okay. So then one uses stability plus compactness, because you're supposing sigma prime is stable, and compactness of stable Riemann surfaces to reduce the maximum case. One sort of very normalized by isometry takes limits and reduces to this situation here. That's a contradiction. Okay, that's all I wanted to say. Thank you.
So, any questions? Any more questions?
In the quasi-function manifold, so you have this low surface in between, but you can select the one which provides the minimum of the area for all the surfaces.
Yes.
Do we know that we are limitless for this one?
You mean the absolutely area homotopy class? No, I don't think it's unique actually. I mean, the minimizer of the area, I should think about it. I'm sure we don't know this, and I suspect the answer is no.
I have a question about your map and Teichmüller. If you just go to the base and Teichmüller, just look at conformal structure, is that true or no? Is it on 2? Can you get any?
Yes, you do. Yes, yeah, you do. Well, it's on. No, it's on 2 for a very simple reason. It's just that, I mean, you have your map to potential bundle, project potential bundle, okay. And here, if you take a point C here, in its fiber you have C comma naught, C comma 0, and 0 is clearly realized because this means second fundamental form is 0, so you only have basically to find a group, a Fuchs group acting on H2 with a quotient from a class, which is basically information. But you can refine this question and try to understand what is the two things you can try to understand. So given a point here, because this map you can define not just from almost Fuchs, you can define from almost Fuchs, from entire quasi-Fuchs, and then it becomes non-objective. You might want to understand what the fiber of the point here is, and it's difficult. I mean, if this is 0, then you only have one image, but otherwise you have many. And the other thing you might want to understand is what is the image, and this is basically this theorem. I mean, some information on that is the theorem that the image is always convex. But it's a difficult question. Gabriele is an expert of that. You have this bifurcation phenomena.
I think it was the element of the fiber is multiplicity, don't they?
Exactly. So if you prescribe another element, which is, you have always at least two. You always have one which is unstable.
Yeah.
And that comes from here.
But in your case, you prescribe the boundary condition.
Yeah, it's a different question.
Yeah, that's what.
It's a different question.
Yeah.
Sure.
I understood finally.
Yes, okay, yes. So this is okay. Yeah. It's a different, imposing stability is different in this one. So you're asking whether finding total curvature gives some information? Is that yeah? I think okay. It's clearly a very strong.
Not for pi, but probably.
Yeah, even just some bound.
You need a formally invariant condition, so it's not clear that, I mean, you've got a circle in S2 which only has a conformal structure to that. So you need some statement which is conformally invariant.
Yeah. No, the answer is I don't know. There is one characterization by Bishop who is saying if you have L2 second fundamental form, then you can characterize as the Jordan curve. So it's called Weil-Peterson quasi-circle. But still, I don't think this a priori wouldn't be able. Yeah, Weil-Peterson. Sorry. Weil-Peterson. I don't believe this implies uniqueness. I mean, at least if it does, not by this kind of arguments.
Okay, so let's
Dello seminario.